and it's called the divergence theorem. So I've got the written stuff here. You can either write it or, you know, look at it later on the video when it gets put up. It's called the divergence theorem. And it's yet another way to find the flux. Didn't we take a surface integral, this guy here called the flux, and converted it into a line integral and calculated it that way? So that was taking a double integral and making it a line integral that had the same value. Well, what the divergence theorem does is it takes this surface integral and it converts it into a triple integral. And the value, because this is a number, will be the same value as this guy. The theory of it is horrendously ugly, but you just need to trust me. That's what it is. So what does it look like? Well, it's a triple integral of a guy called the divergence. And to remind you who the divergence is, your vector field PQR again, the divergence is the derivative of this with x plus the middle one with y plus the end one with z. So can you see that's a scalar function, right? It's only got one value, right? It's a single dimension function. And you're going to integrate that. You're doing a triple integral of E. So what is E? So bad drawn picture, but the best I can do. Can you imagine this kind of peanut looking shape? S is the surface of that peanut, right? S is a surface. E is the solid that's inside that closed surface. So you can imagine S is a closed surface. E is the solid that's inside it. And so the triple integral is the integral inside the solid generated by that surface. And these triple integrals typically are much easier to calculate than this guy. And, oh, the last piece, dv. Well, we already know how to do triple integrals. I know it was a while back, but can't dv by simply just be dx, dy, dz, or any combination permutation you like, depends on the situation. Sometimes dv will be in this format here. Can you remember what name we call it when we do this guy in triple integrals? What's the coordinate system called when we use r, theta, and z? Say the word again.
Spherical.
That's going to be a different one, but you're not spherical, but
cylindrical.
Cylindrical. So sometimes you'll make your expression and you'll convert it to cylindrical, right? You'll make it r, thetas, and z's, but you could make it r, theta, and x. It depends on the orientation. And then less likely, but sometimes dv will use this guy. And when will you use this guy? If the solid is a sphere, or at least part of a sphere, right? But typically a sphere, right? You would use this fella here. And you remember the X, the Y, and the Z in spherical coordinate system. It's very messy, but I think there's a couple of questions where that's the one you use. If this region here ends up being a cuboid, right? A cuboid, that kind of shape, you're probably going to use the XYZ version. If the shape, or if the formula has the surface has an x squared plus y squared kind of thing to it, you know, like z equals x squared plus y squared, that kind of thing, you probably want to use the cylindrical coordinate system to make it easier to do. And if the solid ends up being a sphere, then you use the spherical one. So basically, this surface integral becomes this triple integral. So, should get started. So, here is my first example, a bit like homework question 1. F is going to be 3x, xy, 4xz, and the solid E is going to be the region bounded by, what's it bounded by? Oh, x equals 0 to x equals 3, y equals 0 to y equals 3, z equals 0 to z equals 3. Do you see in this question here, you don't even need to worry about what E is. It's pretty much handed to you in a plate, isn't it? So we're being asked to find the flux, right? This surface integral. And that's what divergence theorem allows us to do. Find an easier way of calculating this guy. And it's the triple integral over the region E of the divergence dv. Well, in this case, x is going to go from 0 to 3. Y is going to go from 0 to 3. Z is going to go from 0 to 3. The divergence, right, remember the divergence is this guy with respect to x plus this guy with respect to y plus this guy with respect to z. And since I'm doing this z, y, x, I guess I should do my order z, y, x. Just repeating myself again here. Well, that becomes 3 plus 5x, a z, a y, and an x. Now, since these are all numbers, do you recognize that this one is separable? And so all I'm going to do is the integral from 0 to 3 of 3 plus 5x dx. And the integral from 0 to 3 of 1. And the integral from 0 to 3 of 1. Right, that guy's 3, that guy's 3, and this guy is 3x plus 5/3 x squared, evaluated at 0 and at 3, and I should have given myself more room.
Professor, wouldn't that be a 5 divided by a 2 instead of 5 divided by a 3?
Yes, it should be. That's going to get me 9 plus 45 halves times 3, which is 9. That's going to give me 18, that's 50, 63 halves times 9. That's 7 carried 2, 54. Didn't say it was pretty. I'm not even sure that's right. Because I did it in my head and I did it quick. Does it look good? Right. The method's right. If you go back and look at it and you find out it should have been, 547 over 2 or whatever, you can fix that. Now, would you agree that in this particular case, isn't that triple integral pretty easy to do? And this here, although it might be messy, it's not that bad, right? Compared to other techniques, this guy is actually relatively straightforward. If you wanted to do this particular one by hand, do you realize that this shape is made up of 6 surfaces stuck together? Top, bottom, left, right, front, back. Technically, if you wanted to do it the long way, wouldn't you have to find 6 separate surface integrals? Each one would be one side of the picture. Now, even if each of those 6 were easy integrals to get, there's still 6 of them, right? And it's still going to take you a fair chunk of time to do it. So I'm trying to sell the fact that the divergence theorem is worth the effort. It gets you the question with relatively little work. Okay. Let's have a look at, no. Yeah, let's do another rectangular one. That one's too easy. How about this one? This is like question 3. We're going to get the usual flux thing. This fella is x squared y. This fella is x squared z. And this guy is x, y, z squared. And the surface S, not the surface S, well, they call it the surface S, but really it's the region E, which is the inside of it. X is between 0 and A, Y is between 0 and B, and Z is between 0 and C. Can you imagine that that's basically just a cuboid with X, Y, and Z being A, B, and C, fitting inside the first octant. Right, so we got E. So the surface integral, this guy here, is going to be the integral from x equals 0 to x equals A, y equals 0 to y equals B, and z equals 0 to z equals C. And let's do the divergence. This guy with respect to x, this guy with respect to y, and this guy with respect to z. I'll just call it dv because I don't have a lot of room here. These actually are the same guy, so what I've really got is 4xy plus 2xyz, and I'm doing what, a z, a y, and an x again, that's the order. And that would work. I could do that. I'm thinking to myself, maybe I could do a little bit of work to reduce my workload later. Is there anything you can do to this expression here that might help you to separate it out a little bit? Anything you can do to this?
2xy out of the whole thing.
Yeah, I'm just going to write triple integral this time without writing that, but pretend I had. Yes, take out what you exactly said, and you're left with this guy. Now, what that tells me is, isn't this separable now? So I'm going to do the x from 0 to A, that guy. I'm going to do the y from 0 to B. And I'm going to do the z from 0 to C. And then those 3 answers, you know, dot, dot, dot. I think that's slightly less work. Right, 3 small integrals is normally easier to do than 3 integrals where you use the previous answer into the next integral, and then that answer gets pushed on to the next integral. Are we comfortable with DVs being cubes and cuboids, either with or without numbers? Thumbs up, we are good. So let me jump to a totally new problem. F is x squared sine y, x cosine y, and negative x z sine y. And our region is the solid inside this guy. Oops. And if you're interested, and I didn't know it was called this, at least they're calling it this, it's called a fat sphere. So I'm assuming that if you calculated this thing, it would not be a perfect, smooth sphere. It might be one of those kind of, I'm trying to imagine how you could make it fat, but maybe distort it in one axis more than the other two. Now, that guy there, if you spent your time just robotically going through it, wouldn't you have to figure out how to parameter, how to set up the 3 X, Y, Z values for this? And you would end up with a lot of headache and no real answer. I'm not going to yet. I am actually going to find this fella. And once I find this fella, you're going to realize why this is useful. So my suggestion is, unless it's like one of these rectangular ones, right, the 3 that we've done, especially if it looks weird, just find this guy first. Well, you differentiate this with respect to X. Then you add, well, if you differentiate this with respect to Y, you get a negative. And then you differentiate this guy with respect to Z, and you get this guy. Wait a minute. Isn't that 0? Agreed? So when I have to do the surface integral, the flux fella, I know he's going to be the triple integral over the region E, this fella, of the divergence dV. But isn't that going to be the triple integral of 0? And when the thing that you're doing a triple integral is the number 0, it really doesn't matter what that region is. Agreed? Because isn't the answer 0? Now, if you weren't looking for that, couldn't you you could spend a lot of time trying to figure out, how am I going to describe this? Is it going to be, Z equals the 8th root of 64, take away x squared plus y, minus y squared, and then you move on to the other one and you do a y equals square root, and then the last one, x equals, what would it be? Probably -8 to +8 or something, right? And really making life hard for yourself. So a little piece of advice, because there's more than one question like this. Find the div of f first. You're going to have to get it anyway. And if it's 0, hey, the answer's 0. You don't need to go any further. Interesting. So I'm trying to think of, if the flux is 0, and I'll try and imagine, I'm just trying to visualize what the heck that would be. So I know this isn't the shape, but just in general, if the flux is 0, and we're talking about the surface of this shape, on the surface of this shape, you've got your vector function f, right? But won't some vectors be pointing into the shape, and other vectors will be pointing out of the shape, all the way along, underneath it, above it, and whatever? If the flux is 0, do you know that kind of tells me, if you think of this as being like a membrane, isn't there just as much stuff going into the thing as there is coming out of the thing? So that's what I'm thinking a flux of 0 would be, right? There's no net loss or gain. The things that are coming inwards, right? The vectors that are pointing into the solid are balanced by all the other ones that are pointing out of that solid. Would that make sense in physics anyway? Could something like that actually? happen, I guess. I don't know how you would make them. If you got a North Pole and a South Pole magnet and you put them really close to each other, would that place in the middle be like a zero flux? Don't know. If you're saying something, James, I can't hear you. Sorry. No, you're just thinking out loud. Gotcha. Okay, let's, who should we do next? Let's see. What's that one look like? Question 9.
Wants to take attendance while you do that?
Yeah, good idea. Take attendance right now. I'm going to set up, looks like question 9. I've done enough cuboids. I want to move on to do cylindrical coordinates. I think this one's going to be cylindrical. Okay, is that everybody taking attendance? We good? Okay. Go away. So we have a pretty nondescript vector function. E is a solid bounded by this shape. So evidently that shape is, I don't know what it is, but it's bounded by it. Excuse me. And they're actually asking you get the flux. So I'll stick to my little rule just in case this one is going to be a zero guy. I strongly suspect it's not. If you differentiate that with respect to x, you differentiate that with respect to y, and you differentiate that with respect to z, it looks like you get what, 3x plus 1? Double check that, 2x, x, and 1. Looks good? Okay, so this is the problem. We need to set up a triple integral limits of integration on a guy that looks like this. Do you see these x squares and y squares? These two guys? They're going to be the guy that I'm going to be looking at doing cylindrical on. Okay. And in this particular version, Z is Z, right? That's what happens with cylindrical. Z stays as Z. Now, what do I have? Well, if you look at this shape and you're trying to figure out what it looks like, don't you drop it to the floor, the XY plane. Good. And if you drop this fella to the XY plane and a little bit of rearranging, isn't it x squared plus y squared equals 16? So that tells me that the r is going to go from 0 to 4 and that the theta is going to go from 0 to 2 pi, right? So I've already set up, well, I guess I should do the whole thing over here. So our surface integral, the flux, is going to be a triple integral of the divergence, which we already have found. It's going to be r, dr, d theta, dz. I might rearrange that order, but right now I'll keep that one. R is going to go 0 to 4. Theta is going to go 0 to 2 pi. And Z, Z is going to have to be figured out in terms of R. Has anyone got any ideas what Z would look like, what the range of Zs would be?
Would it be from 0 to 16 minus r squared?
You nailed it. Okay, tell me why the 0.
We lost your share.
Okay, what the heck am I doing? Can you see it now?
Yes.
Okay, tell me why it's 0. You're correct, but what made you know it was 0? Or maybe it's just obvious that it's 0. I'm pretty sure I know where the 16 take away r squared comes from, right? Is it not just r squared? If you're looking at this shape and it's on the floor, isn't the floor z equals 0? That's essentially it. Okay. Now, in this guy, the way I've set it up and the order I've written down the integrals, I do need to tweak things. Plus, I don't leave 3x, do I? Right. So let's see if we can tweak things around a little bit. I'm going to keep the r equals 0, r equals 4, and I'm going to keep that because technically, aren't they totally interchangeable? It shouldn't really matter, I'm assuming. And this is going to be 3r cos theta plus 1 times r, oops, and I forgot my z equals 0 to 16 take away r squared. So that means I'm going to do the dz first, the d theta second, and the d r last. Why does dz in particular, why does dz need to be first? I could switch the theta and r and it wouldn't matter, but why must I do the z's first?
Because in their limits, there's an r, and you have to do that first.
That's the reason, right? Typically, you should only have one thing with a variable in these questions. So if something's got an r in it, in this case, it's got an r, but maybe next time it'll have a phi in it or something, you would do that one first. And at this point, can I just dot that? Because it's pretty much, you know, it's pretty standard triple integral. Do you know what? I'm getting really good at saying triple. I'm really pleased with myself. It's a hard one to say. Let's pause for a minute and get this out of my head. Do you know that I say R with more R sound in it than probably you do? Are you used to me now that we're well into week 11? For some of you, it's the second or third time. Do you even hear that anymore? True story. I was on Wednesday when I had my conference day. One of the conferences that I viewed or took part in, it was showing me how you can actually get, I think it's Penapto, you can actually get it to do, at the bottom of your videos, your text as you talk. It's not very good with my accent. Because I got one of our videos and asked it, you know, and just looked at it. And about every fifth word, it turned into some other word, right? For instance, 6 is sex, just to give you an example. And a couple of the others I will not even tell you. But if I put closed captioning, whatever the damn thing's called, mothers would be complaining to the school about my language. Because if you ever did this, do you ever get a song where you mishear the lyric and you put a different word in? Or somebody tells you that that word is something. And from now onwards, whenever I hear that song, I always hear that word, even though that's not what the singers are saying. It's like that. Once you see the text, you do think I'm saying that word. It's really weird, and I know I'm not, and that's my ears, and I'm going, God, is that what it sounds like? Are you lot used to me saying 6, for instance? And that's what you hear? Good. Phew. I'm drifting because I can. I'll get this out of my brain, then we can get on with it. There's a Christmas song that I do exactly that thing to. And one of the lyrics, I'm not going to sing because I'm hopeless at it, is, you know, so this is Christmas, right? And Happy New Year, that one. And the lyric at the end, or part of the lyric says, what's it going to be like Christmas without any cheer? And I hear without any beer. And I can't, that's all I hear now. And I'm thinking, yeah, you're right. Christmas without any beer, that's just not a Christmas at all. Anybody got a song where a lyric, you hear a different word and you always thought they were saying this, and then someone explained they were actually saying something else?
I still have yet to understand everything in Rocket Man.
There are words that don't make sense to you yet? Okay. You're showing your age, James, you know that?
I used to think the song Panama by Van Halen was Canada when I was little.
Okay. See, I've got you poor. Not only am I distracting myself, do you realize I've now successfully distracted you a lot as well? So, whew, are we all looking at the white screen? My hand in the paper? Okay. I'm going to show you another cylindrical one. I'm looking at it here, and this is version of question 11. God, what's the time? Oh, got to get move on. In this case, the vector function is, God, that's messy. Cosine of z plus xy squared, x e to the negative z. Oh, I can see what's happening, okay. And then it's a sine y plus an x squared z. So far, so good? The surface, which is going to be our solid, is bounded by this guy. That's going to be my solid E. In this solid, where is the clue that I'm going to use cylindrical?
X squared plus y squared.
Right. Now, I know there's a question, and I know I won't have time today to do it, but there will be another one. Now, that is basically the same shape, but they've orientated it differently. That also counts as cylindrical. Right. You're normally used to seeing it because most questions are in that form, right? X squared plus y squared. But any combination of two variables squared will be a cylindrical. If you were going to do this one, you would just leave x alone, and you would do z and y, and you can choose who you want to be the r cos theta and who you want to be the r sin theta. It typically won't make a darn bit of difference. You'll still get the same answer. Right. Now, back to the guy that we've got. If somebody can remember tomorrow to ask me to do another cylindrical one, but with, you know, like an x equals y squared plus z squared kind of guy, I should do that. Right, in this case here, won't we call x r cos theta, because we typically do that. Y will be r sin theta, and z will be essentially z. And in this case, won't this guy, when you place it with z equals 4, don't you get x squared plus y squared equals 4? And that tells me that r is going to be from 0 to 2, and that theta is going to be 0 to 2 pi. Are you happy about how we got the limits of r and theta by combining these two together? So I should have probably did this one first, because it might have been 0. And if it had been 0, I just wasted a whole load of time. It's not, because I can see an answer here. And if you do this guy with respect to x, that doesn't matter. All you get is 2xy. And if you do this one with respect to y, it certainly doesn't matter. And if you do this guy with respect to z, you get that. So it ends up being 2xy plus 2xz. So our surface integral is going to be this triple integral.
Wouldn't it be x squared instead of 2xz?
Did I screw up somewhere? This one here?
Yeah,
Thank
I
you.
was thinking
Yeah.
the same thing.
Yeah. Thank you. I think I differentiated the wrong guy, didn't I? There. So we're going to have a 2xy plus x squared. And we've already decided it's an r dr d theta dz world, right?
Wait, so for x, wouldn't it be y squared?
Oh, God in Himmel. That's a world record for screwing up. All of the bits except 0 are wrong.
Oh, well, it makes it easier now.
It does actually make it easier as well. So, but I guess I shouldn't fault it. My limits integration, for no particular reason, I'll do the r on the outside because it is a number. And I'll do theta next to it because it is a number, but you can swap them around if you want. We have to figure out a z. And I got a 4. And I got this guy.
Wouldn't it be 0 to r squared?
Will it be 0? So it's going to have something in it. I'm checking with my solution here. It's not 0, which I pretty much assumed. The reason it's not 0 is that it's this and this. So can you imagine a cone being cut off at a height of 4? Right, it's actually an upturned cone being cut off at this side here. So the answer is going to be this way round. Small guy, big guy. How do I know this is smaller than that? Because I could have written 4 to r squared. Isn't the range of r between 0 and 2? Won't r squared be a number between 0 and something less than 4? Won't that make r squared small and 4 big? That makes sense? Right, okay. We got this fella here. So it's 0 to 2, 0 to 2 pi, z equals r squared to z equals 4. That guy is actually r squared, which makes this guy r cubed. And we'll do the z first, the theta second, and the r last. And I think that's a dot, dot, dot now, isn't it? Are we good?
Yeah.
Any questions? Are we good? Right. I haven't done a polar, but I definitely will do that tomorrow. But can you imagine you have an E and it's x squared plus y squared plus z squared equals 25. Imagine the solid is a sphere. If you see E and it's a solid, you know, it's a sphere, then that means we're going to have to do the spherical coordinate system, right? So although we haven't done one, can you imagine it's going to be easy to tell the situation where that's going to happen. Now, the spherical is a pain in the butt because don't you have to know an X, a Y, and a Z transformations, and they're not as simple like r cos theta and r sin theta, right? You have to do all the details to it. And we are done for today.